Okay, so what I want to do now is I want to talk about emergence as a phenomenon in science, and I'm going to talk about why you should take these two courses, Emergence and Phase Transitions, which is this quarter, and Spring Emergence and Order, which is a separate course. So let's talk about what this course, the one you're taking right now, is, what it's all about. And I try to think about what this course really is about, what is the unifying principle. And I realize that the unifying principle of this course is that everything in it is impossible. Okay? Nothing in it, it would be the sort of thing that if you didn't know it, you would say this can happen. So that's the first thing that I'll show you, is that emergence should not happen. There should not be order. You can easily see why that's not why that's surprising. So when we use basic statistical mechanics, we will find that, well, it seems that emergence shouldn't happen, and you can easily prove it. And we're going to see that, in fact, that's not quite correct. The reason why emergence even happens, why you have phase transitions, why you have ordered states like magnetic states, superconducting states, and so on, the reason is incredibly subtle and was certainly not understood properly even, I don't know, 60 years ago, 50 years ago, something like that. We're going to see that most of the things that you assume as just taking for granted in science don't work either. So, for example, linear response theory. So what do I mean by linear response theory? Suppose I have a magnet, and in this course, we will mostly be thinking about magnetic systems as examples. So a magnetic system that we will often use is a magnet on a lattice, and we will define this later on. But for now, just think of the lattice as having electrons that have spins, and those spins can be pointing in up or down directions. So we think of it like that. And now you might imagine that you apply a magnetic field in, say, the Z direction, and you might say, well, what's going to happen to the magnetic spins that are there? Well, what you would expect is that those spins will interact with the electronic dipoles and align them. And so when you apply a magnetic field to a system, you expect that the system will become magnetic. That's how you make magnets. And similarly, if you take your magnet, stick it against your refrigerator door, it'll stick. If you take your magnet, put it in the oven, heat it up to a very high temperature, probably higher than your kitchen oven can do, and then let it cool down, and then stick it onto your refrigerator. It will not stick. Okay? Now, we're going to understand why all that happens, at least somewhat. But the thing you would say is, if I apply an external magnetic field to a magnet, how much will it magnetize it? And you would say, well, I don't know, proportional to how much magnetic field I apply. If I apply a weak magnetic field, it will magnetize it a little bit. If I apply a strong magnetic field, it will magnetize it much more. So you would say, okay, the amount of induced magnetization should be proportional to the external field that you apply, and it's actually divided by KT. And this law is known as Curie's law. Okay, and it's just obviously, it makes sense. And you also know that this probably isn't true if the field is very strong. So there might be higher order corrections which would come in there. And in fact, later on, we'll compute what this function looks like exactly. Here's the thing. And a phase transition, that law breaks down. Linear response theory, which is just used to seeing everywhere in physics, doesn't work at phase transitions. And that's another thing that goes wrong. Okay, perturbation theory. Okay, so you've been taught quantum mechanics, hopefully. Maybe you've been taught classical mechanics. You know that as I take a physical system and I have a version of it that I can solve exactly, like, say, a hydrogen atom, and then I want to say, well, what happens if I add an electric field or a magnetic field to a hydrogen atom? That's going to change the Hamiltonian, it's going to change the eigenstates and stuff like that. And you know how to compute that using perturbation theory. Well, guess what? You can do the same thing in statistical mechanics, but at phase transitions, it doesn't work. It breaks down. In fact, you'll hear me say this quite often, perturbation theory is only interesting when it breaks down. The only use of perturbation theory is to tell you when it breaks down. And why is that important? It's important because the breakdown of something tells you that something that you've assumed as taking for granted is not true. When you're doing perturbation theory, you're perturbing about some particular state of the system. You might be perturbing about, say, the gas state or the liquid state of the material, and you're trying to understand the solid state. If the perturbation theory breaks down, it tells you that your starting state is not really a very good approximation to the thing you're trying to calculate. So the breakdown of perturbation theory, in fact, tells you much more information than if perturbation theory actually worked. And so that's why I say perturbation theory breaking down, which it does at phase transitions, is very important. Okay, here's another thing we're going to learn that doesn't work. And I want to just check on something before I go any further. I just want to check that my microphone is on. So, because if it isn't, then no, the microphone is on, so we're fine. So the next thing that happens is dimensional analysis breaks down. So you've probably learned about dimensional analysis. How many people here know dimensional analysis? Okay, we'll see if you really do. Okay, in a few minutes. Okay, but you've learned it, and you've probably either not learned it correctly or you've heard inflated claims about it. And we're going to see that from some people's perspective, dimensional analysis breaks down at phase transitions. And why does it break down? It breaks down in very surprising ways, and that breakdown violates common sense. And I'm going to keep this as a mystery until a little later in the quarter, because the way that this happens is truly surprising, and it's so surprising that when this problem was solved, when the problem of phase transitions was eventually solved by a renormalization group, the person who solved it got the Nobel Prize in Physics, Ken Wilson. Okay, there were two other people who also should have shared in that prize, but that's another story. But Ken Wilson got the Nobel Prize not just for solving the problem of phase transitions, which, as you'll see, is a very limited kind of problem, but because thinking about what was going on in phase transitions totally changed our perception of what is going on in all the physics. Our complete understanding of physics, and in fact of science itself, changed as a result of the renormalization group. There is now a whole school of the philosophy of science that emerged from, well, I don't want to sound immodest, but philosophers of science who read my book, read papers by Michael Berry, papers by Leo Kadanoff, and realized that what the perspective that the renormalization group created actually undermined the way that philosophers of science believed that was the nature of scientific explanation. So, and all of this comes down to the way that these things, like dimensional analysis, break down. So we're going to see, and we'll talk about this in our second lecture, the breakdown of small, so negligible. Usually if something is small, like say 3 orders of magnitude smaller than something that you already know how to calculate, you would say, okay, well, it's small, so we can neglect it for now. Common sense. That's how you've been taught how to do physics. It doesn't always work, okay? And phase transitions are where that doesn't work. Then the other thing is I'm going to show you that we can make very precise predictions. I'm going to show you this today. We can make fantastically precise predictions that agree with experiment, but we're going to make those predictions based on ludicrous models, ludicrously simple starting points. And this is why the philosophers of science got so angry, as it were, because the usual idea was, well, I've got a theory and it makes a precise prediction, that theory must be correct. And then you have to look at that theory and you think, well, okay, now I understand something about the world. What we've learned from the renormalization group is that's not true. You can make precise predictions knowing very little, knowing virtually nothing. And so you have to understand that this isn't always the right way to be thinking about what is going on in science. So we'll talk a little bit about that. So who cares about phase transition? Okay, well, you should care. So this is the phase diagram of life. This is from a paper I wrote in 2017. I'm not going to go through why it is like this, but what it shows you here is on the vertical axis time, and it's showing you the phases of life. So there's a thing at the middle of the phase of the picture there called LUCA. That means the last universal common ancestor. So one of the pieces of work that I did that became quite well known in the origin of life literature was to answer the question, how is it possible that the last universal common ancestor of all life, which we know is dated to about 3.8 billion years ago, how did this evolve so rapidly? So let's just put some time scales up here. The world started about 4.6 billion years ago. Okay? This is 3.8 billion years ago. This last universal common ancestor is a mythical organism. It might be an organism, it might be a community of organisms. And from that organism, all life descended. And this, in outline, is the family tree of all life on Earth. It's not quite correct, because we now know that eukaryotes, at least many of the eukaryotes, kind of emerged from this branch of life called the archaea. But it's close to being correct. And this is how it was understood back in 2017. Now, so this organism, from this organism, all life descended. And we know this is true because we can construct the family tree of living organisms by comparing their DNA sequences and looking at genes that code for a part of the ribosome, a machine in every cell, in every living organism that we know that produces proteins. And so what we know is that this last universal common ancestor, we can detect its existence, and we look at its genes, we know that it had the architecture of the modern cell. Okay, but it had it 3.8 billion years ago, less than 1 billion years after the planet was formed. For most of that period of time, the planet was completely inhospitable to life. So the question is, how did the last universal common ancestor of life evolve so rapidly? And then you think about 3.8 billion years ago, this is a very weird timeline, because this time is short compared to the time between Luca and where you are, somewhere over here. So evolution then slows down. How is it so fast, and why is it so slow now? And what work that I did about 20 years ago was on how the genetic code, the code that tells the cell how to take triplet codons of DNA or mRNA and construct proteins, that the code book that tells you how that works, that code book evolved, and we discovered how it evolved, and the way it evolved was through collective effects, indefinite effects. One of my collaborators, Carl Rose, called the progeny state. So there was a state of life where everything was collective. Organisms talked to each other. Right? The way they talked to each other was they just absorbed each other. And then they took in the cells themselves, took in their DNA and everything, and genes and protogenes were swapped during that process. Today, that doesn't happen. You have individual organisms and eukaryotes, bacteria, whatever, and you might think, well, that sort of process, that collective process doesn't happen, except actually it does still happen, but it happens in a different way. I'm not going to go into details about that for this course, but I just want to point out that this is the model of all phase transition. This transition from the collective stage of life and the more individualistic stage of life. Now, this course, we'll say modestly, might be the most important course you will ever take. Oh my goodness, lower screen. So this will be the most important course you will take. Why? Because you're about to live through what could be the most appalling phase transition in history, a global climate change, which will have many effects, both in terms of climate, in terms of its social impacts, in terms of culture, many things like this. And what people would like to understand is how these phase transitions in climate systems, regime shifts in ecology, how those things occur. Right now, there's huge interest in the ecological literature of trying to take what we know about phase transitions and apply that to help us be able to predict what happens in ecosystems. People, you may have heard of the phrase in the popular media, tipping points. People call them tipping points, like in a forest might have a drought and then they eventually turn into a desert. It's called a tipping point. But basically, these things are essentially connected to phase transitions. And what we want to understand is, how do you predict them? How do you classify them? How do you understand what are their properties? How do you predict how they're going to change in time and so on? And so understanding global climate change and the consequences of that is something that to which phase transitions and phase transition thinking will become increasingly important. Yes, question.
So how do we compare the climate system with the previous Tree of Life, where you talk about the phase transition between communities and individuals?
Yeah.
And the climate, I think, is more individual or community.
Well, that's a good question. So I think that there are collective effects in climate as well. So because you have collective interactions between, say, fluid mechanics, say the atmosphere, the oceans, the animals such as humans. I mean, after all, the global climate change was caused by humans. Okay, it wouldn't have happened otherwise. And so you already see that there are these interactions between the population biology, as it were, and the physical oceanography, the physical atmospheric science, and so on. So to understand global climate change properly, you have to understand those things. But it's not just that. It's also social science and economics, because a lot of the things that are happening in global climate change are a result of economic choices and social and cultural choices that we as a community have made. And so whether or not one can control it, one can understand it, and so on, depends on understanding all of those things. Those social and cultural interactions are very collective. So did I answer your question? I mean, of course, you want to give a whole course on what I just said in the last 10 seconds, but I'm not going to do that, and I'm not qualified to do so. Most of what we're talking about, the most interesting aspects of this are for complex systems. So let's talk about what I mean by complex systems. So complex systems are, what I mean by complex systems, before I get into what characterizes them, people sometimes say that I'm a condensed matter physicist. Condensed matter physics usually means the physics of stuff that is dead, for one thing, and the physics of stuff that is in equilibrium, like a lump of salt just sitting here in equilibrium with a perfectly regular cubic lattice. Okay, those things are pretty boring. They're pretty simple. And the reason that we know everything about them is because every question we can ask about those things is a really easy question to answer. I mean, it's not to say that they're not complicated, but they're not complex. The things that we're most interested in are complex systems. So they're systems which have strong fluctuations. So they're not just sitting there with, little small fluctuations of the atoms about their average positions. They're doing all sorts of crazy things. They have unpredictable and nonlinear dynamics. So think of fluid turbulence as an example. There's multiple scales of space and time. So think of fluid turbulence, for example, which has scale invariance. They have emergent structure. So think of fluid turbulence, for example, which has structures of vortices and swirly-whirly bits of fluid that emerge out of nowhere, like hurricanes and things like this, tornadoes, even just swirly-whirly things that you can see in your bathtub when you put your fingers in and stir them up. So there are structures, coherent structures that emerge seemingly out of nowhere. They may be active, meaning like they're out of equilibrium, like you, for example, are powered by the sun. You're powered by the sun, and you convert the sun's energy into electrical energy, and that makes you work. You're an electric device powered by the sun. You're active. There's lots of feedback loops between things. That's why everything is nonlinear. There's multiple layers of system dynamics. So going back to your question, we have the physics of the atmosphere, Navier-Stokes equations, but then you have to worry about the terrain, you have to worry about the effects of vegetation, you have to worry about the effects of clouds, you have to worry about human activity, etc., etc. So there's multiple layers of systems dynamics that all interact with each other. Yes?
Can you give us some examples about like how the scales of the space affects the power of the system?
So the question is, how do the scales of space affect the properties of the system?
Yeah.
So what we're going to see in just even simple regular phase transitions is that the reason phase transitions have the interesting properties that they do is that there are multiple scales within the system. In fact, most systems, the simple systems that you're used to, have been taught about already, usually just have one physical scale. Like, say, the orbit of a planet around the sun. There's just the radius of the planet, and you think of the planet as being a point particle just orbiting the sun. Okay. Complex systems have multiple scales that interact with each other all the time. So if you think about a picture of fluid turbulence, and it's forward over here, so here's a picture of fluid turbulence. Okay, multiple scales. Water sees swirly things on all scales, and the large scales sweep the smaller scales around with them. Okay, so all these scales interact. So the reason why you've not been taught about these things up to now is the same reason why they weren't studied until now. Why? Well, in the natural development of the sciences, the sensible thing to do is to do the easy problems first. Okay, so what happens when you throw a tennis ball? Okay, we didn't know the answer to that question until Isaac Newton figured it out. Okay, and that was only 400 years ago. Okay, roughly speaking. So these are very simple questions. Even those turned out to be very complicated, and we can say, well, a tennis ball is just a point particle. We just shoot it with our hand, and it flies up and it goes into some sort of parabola. And so you can understand that, and then you start to think about, well, everything is really just particles. So we think of stuff as made up of particles, and then we say, well, if I want to understand how stuff works, all I've got to see is what it's made of. Okay, that's called the reductionist approach to science. So I want to understand how a fluid flows or how a tennis ball flies through the air. I just need to look at what are the atoms and molecules that make this thing up. That's called the reductionist approach. Well, when you look at fluids, for example, so you look at a turbulent fluid like that one over there, you all looked at that picture and you said, yeah, that's roughly what I think of it when I think about turbulence. Leonardo da Vinci, one of the greatest artists in history and also a great scientist, has a famous picture of turbulence which looks kind of like mine. He's a lot better artist than I am, so his is a bit more accurate than mine. But one of the things that you didn't ask when you looked at that picture was nobody said, oh, by the way, what is that fluid? Is it water? Is it liquid nitrogen? Is it alcohol? Is it Coca-Cola? Okay, that doesn't matter. Okay, they all do the same thing. Doesn't matter what the stuff is that they're made of. Okay, so then you start to wonder, well, okay, when do I need to know what stuff is made of, and when not? So anyway, complexity. We understand that we do the easy things first, so we learn about reductionist things where we can say, I want to understand the structure of matter. Okay, just look at the atoms, and then you say, well, okay, atoms actually aren't the indivisible building blocks of matter, which the 19th century chemists told us. So then during the 20th century, the dawn of the 20th century, people discovered that atoms have a nucleus, they have electrons. The nucleus is then made out of neutrons and protons, and those neutrons and protons are made out of mesons and so on and so forth. And so we actually understand, and I'll talk a bit more about this in a few minutes, that what we think of as being particles actually aren't particles at all. And so then those things that we think of as being particles are actually collective entities. Okay, how about you? Okay, let's have a look at let's write down the names of some of the elementary units of matter. Okay, so you might say, okay, well, there's photons, electrons. You start to see a pattern here. You probably don't need ChatGPT to tell you the common thing and all of that. And then you might say, well, okay, let's apply this into the realm of biology. So you might say persons. Okay. Individuals. Okay. Are they? Are you really an individual? Well, no, you're not. You're basically, if you want to think about yourself, think of yourself as a traveling zoo. Okay. If you look at your eyelids, you've got little creatures that live on your eyelashes, and they live there and they crawl around. And if you have too many of them, they make your eyes tear up on a windy day. Okay, how many people here have discovered that for themselves? Okay, you have little mites that live on your skin, in your guts. You have bacteria. You have, in fact, 10 times as many bacteria cells in your body as human cells. Okay, so if I were to say to you, "Are you human?" the answer is, well, numerically speaking, you're bacteria. You've got 100 times as many bacteria as genes that are bacterial as you do human. So no, none of these things are individual. Everything is made out of other stuff, and who knows where it stops. There's a lot to say about who knows where it stops. So the point is that eventually all of these things interact with each other, and so you get emergent phenomena, and then we get complexity. Okay, so where does all this start? Okay, so here is a scientific paper that had an enormous influence. It's by Philip Anderson, who won the Nobel Prize in Physics for his work on localization. It's called More is Different, paper published in Science. And he says, he pointed out that the reductionist hypothesis is not really correct. And he talked about spontaneous symmetry breaking, phase transitions. We'll talk about that in this course, and how, in fact, understanding it changes the whole nature of the way that we think about science. So I'll put that article on Teams, and you can read it. It's a fascinating article, very easy to read, and it really reflected a sea change in the way that physics was done. So let's think about the history of physics. History of physics is basically like this. So Newton figured out classical mechanics about 400 years ago. Then sometime around the earlier part of the 20th century, people figured out quantum mechanics. Sometime around the 30s and 40s and 50s, people realized that the stuff inside other stuff and the stuff inside that stuff and so on. People started discovering the zoo of elementary particles, which have got stuff inside them, just like you've got stuff inside you. So they weren't really elementary particles at all. And that was the progress of science, going to smaller and smaller scales of space, smaller and smaller scales of time, and larger scales of energy. Okay, that's what we think of as being physics. But around about the 1940s, there was a separate branch of physics that started. So that branch of physics was called condensed matter physics. And I used to be at the University of Illinois, which is one of the birthplaces of condensed matter physics. So let's think about physics in the following way. Here is the macroscopic world. And those are the things that we can see with our eyes. And then gradually we invented microscopes, and then we invented optical microscopes, and then we invented electron microscopes. And then we invented high energy accelerators, which are basically just another name for a big microscope. And so we could get down to smaller and smaller scales, or I don't know, I'll say nanoscopic, just for example here. And so all of this is what we do in physics. We go to small space, time, and large energy. So that's basically what we think of as being physics. So what happened in the 1940s and so on? 1940s, people started doing kinetic matter physics, and so they said, well, let's start here. Let's say this is solids and this is electrons and solids, for example. And then let's go this way. Let's start at this scale of description, this level of description, as I will call it. And then let's ask, if I know what stuff is made of, how do I get to predict the macroscopic properties of matter? So this is if you predict macroscopic going this way, understanding what these things are, this you can think of as being high energy, or whatever you like to call it. Okay. So this kind of started around the 1940s. One of my colleagues at the University of Illinois at Urbana-Champaign, where I used to be for 36 years before I came here, was John Bardeen. How many people here have heard of John Bardeen? 1, 2, 3. So, okay. Okay, for those people who've heard of John Bardeen, how many Nobel Prizes did he have? He had twice as many as Albert Einstein. Okay, he had 2 Nobel Prizes both in physics. Okay, his first invention you use every single day. Most of you are using that invention right now. That was the transistor. Okay, everything you're using was powered by transistors. That was his first one. His second one was for the theory of superconductivity, which we'll talk about not so much this quarter, but in the course Emergence and Order, we will talk about the theory of superconductivity, which was his second Nobel Prize. So in the 40s and 50s, this field started at Urbana-Champaign and other places. Some of the first textbooks in condensed matter physics were written by people like Fred Seitz and others. And this field starts off at this. Well, I want you to remember this term, this level of description. I'll ask if you know what stuff is made of, how do you get up here? In this way of doing physics, as it were, going from large to small, it's basically assumed that if I know what everything is made of, all I have to do is just put it together. Okay, that would be like saying, you can think of a high energy physicist of taking a watch and just smashing it with a hammer, and all the bits fly out. And they say, once I saw what all the bits are, I know how a watch works. Okay, actually, a high energy physicist would never do that experiment. Okay, a high energy physicist is much smarter and would not take a watch and hit it with a hammer. They'd take 2 watches and smash them together because in that central mass frame you get more energy. Okay, so seeing bits that fall out doesn't tell you how they're put together. Okay, that's what condensed matter physics does, and that's what Phil Anderson was talking about here. Okay, so now let's talk about emergence. So I want to do an experiment. Okay, so physics is an experimental subject, so let's do an experiment. Okay, so here's what I want you to do. Okay, I want you to get your finger, or the first finger, please, and I want everybody to push up and see if you can move the ceiling. Okay, okay. Anybody succeeded? No. Anybody feel a little bit of the ceiling pushing back? Like no. Okay, that's experiment number 1. Okay, so none of you were able to move the ceiling. Here's experiment number 2. This is the controller for the projector. Now I'm going to do something really amazing. Can everybody see? Because I don't want you to miss this. You're going to see something that is the most amazing thing you've ever seen in your whole life. Okay, so can you see over there? Okay, watch this. Look at that. Do you see it? Let me do it again. I was able to push it, the whole thing. Right? Now, I didn't let you do that experiment. That one's too dangerous for you to do. I just let you do the pushing up experiment. Okay, so what this is really a very strange thing when you think about it. Okay, why was it that if I push with my finger like this and pushing into the air, I didn't transmit a force at all. But when I pushed this thing, I was able to move the whole thing. Okay, it's like the atoms decided that, well, we could just sort of get out of the way of this finger, but actually we'll just conspire to stay in the same place with respect to each other. And we will let somebody over here push this atom, that'll push this atom, that'll push this atom, that'll push this atom, that ends up pushing 10 to the 23 atoms. Okay? And it didn't happen when I did this. Why? Okay, and this is something that's bizarre, even more bizarre than you imagine. Why? Okay, so here's a box. This is the sort of physics version of what we just did. So here's a box. There's a bunch of atoms in the box. You can think of the box as being this room. There's these little atoms floating around in it. That's the fluid state. And you know that if I take this box and lower its temperature, the atoms will form into a crystalline solid, right? Okay. So you might say, well, you know, this is the solid state. It's something that is emergent. It has different characteristics from the fluid. It has a periodic crystal lattice. I can try to shear the solid. Like if I take this and try to shear it, well, you know, if I could break it if I pushed it hard enough, which I'm not going to do, obviously. But it resists deformation. Whereas if I take some air and just try to move it around, there's no resistance at all. It doesn't fight back. So this state has different properties than the fluid. But the thing that's interesting about this is that the underlying physics of the crystal is exactly the same as that of the fluid. Okay. When we do physics, the first thing we do in quantum mechanics, let's say, or classical mechanics, is we write down the Hamiltonian. The Hamiltonian is the kinetic energy plus the potential energy. The kinetic energy is just things moving around, and the potential energy is just the forces between the atoms. The interactions between the atoms are exactly the same in the fluid as in the crystal. Nothing changed, okay? But yet, the macroscopic behavior is completely different, even though they have exactly the same Hamiltonian. Okay? So something interesting has happened there, and we need to understand why. So that argument says, okay, well, let's think about this. First of all, the pairwise interactions between atoms did not change. The correlations, though, between them definitely did change when we lowered the temperature. And it's as if the solid state emerged by magic out of the fluid state. How did it emerge? Okay. Now I'm going to make another startling claim. So we know this is true because we've all seen it. But I'm going to make this next outrageous claim. I'm going to claim that the solid state has its own new laws of physics. But the laws of physics, what we call the laws of physics, are different for the solid than they are for the liquid. And you may say that can't be true because they have the same Hamiltonian. You just reminded us of that. Well, let's have a look and see what is the textbook picture of a solid. So let's suppose you go and open up a standard textbook on solid state physics, elementary solid state physics, like say Ashcroft and Lerner. How many people here have had some elementary course on solid state physics? Yeah, most of you have, many of you have. Okay, so you say, well, we just start off with the atoms, then some crystalline array like this, then we have some strings between them, and you know that if you can have phonons, which are basically quantum sound waves that go between them. And so that's your picture of the solid. That's very different from the picture that I had on the previous screen of just bunch of particles bouncing around in a box. But it's the same thing. And what's happened here is that the solid state has its own new laws of physics because it has new long-range forces between the atoms. Those long-range forces are the elastic forces. So if you want to know what is emergent about the solid, the thing that is emergent are these springs. these springs between the atoms, which is the starting point of every discussion in a solid state physics textbook, those springs are emergent. They came about through collective interactions between these things, and we need to understand that. Most textbooks on solid state physics would start off with this, it's like it's self-evident. Nobody ever starts off a textbook on solid state physics by saying, let's work out the properties of sodium chloride crystal, starting off with this picture. You always start off with this picture. So there's new long-range forces that are completely distinct from the original forces from the atoms. We call those things elastic forces. They tell you about the response of the solid to perturbations, and those external disturbances, the way the solid responds is completely different from a fluid. If I take something that is solid and I hit it, it makes a noise like that. That's Hooke's law in operation, sound waves propagating through it. Doesn't happen when I try to hit the atmosphere. Okay, so you've got very different laws of physics. And the origin of these new laws is collective. It's the statistical behavior of the atoms. And we know it's the statistical behavior because when we heat this thing up, eventually the atoms decide, actually, we'd rather be on our own rather than coupled to all the other atoms in the system, and poof, this thing melts. So it's really true to say it has its own new laws of physics. And you say, well, really? I mean, a high energy physicist would look at a solid and they'd say it's just the same thing as anything else. Well, at the level of description, so the interactions between atoms cannot be detected. When you look at a solid, and people who looked at solids did this in the 19th century, people like Cauchy and Maxwell and others, they were trying to understand the elastic behavior of solids. And that was called continuum mechanics. Okay? They didn't know about atoms. They didn't need to. They already knew that solids behaved like this. They didn't know how. And they wanted to know, well, if I know I've got a solid, something that can stretch, like a piece of rubber or something like this, well, then we want to work out the physics of that, the continuum mechanics. It's a whole field of physics devoted to the emergent properties of stuff like that. Okay, fluid mechanics, it's the same thing. When they were working out solid mechanics and continuum mechanics, they were also looking at fluid mechanics. Again, we really know that if you look down on fluids in detail, there's atoms and molecules and things like that. So it's very strange because we have a level of description which is macroscopic, which doesn't depend on what the laws of physics are at the microscopic level. So you might say to yourself, let's do a thought experiment. Okay, let's really confuse our colleagues in chemistry. So let's suppose I go to my colleagues in chemistry and I say, you know everything about atoms and electrons and things like this, and molecules and so on, how they put together. Okay, how much of chemistry do you think would change if I told you that the radiative corrections to the mass of the top quark changed because of some new experiment that was done at CERN? Okay, so we know about quarks, we know that we can work out what contributes to their mass, we know that there's vacuum fluctuations that contribute to that. Let's suppose that we did an experiment and we discovered, we've measured this thing much more accurately than was known 20 years ago. My goodness, all of chemistry is going to come, solid state physics is going to come crashing down around us because we discovered there was this error in what we had thought of was the mass of the top quark. Well, of course, the chemist is going to say, well, I didn't give a damn about that. All I need to know is what is the mass of a proton? What is the mass of a hydrogen atom? That's it. It doesn't matter. It's just some phenomenological parameter that they've already determined, and they never need to see it again. When you're doing chemistry, you don't even need to know that quarks and gluons and superstrings or whatever exist. Okay? So in fact, what I've just told you is that this picture of the world is actually completely wrong. This is not the picture of the world. Okay? Let's have a look at what the picture of the world really is. The picture of the world is really like this. There's a microscopic world over here. Number one, microscopic world. Number two over here. Another one over here. These are all possible microscopic levels of description that when you do statistical physics, and of course Raymond, and do all the things I'm going to teach you in this class, you can deduce the macroscopic properties. but they are all different microscopic worlds. Here's one where the mass of the top quark is what it is. Here's one where it's 30% different. Here's one where it doesn't even exist at all, where there are not even any quarks. None of those things matter. Okay? So really what happens is that there's many microscopic levels of description. There's a unique, I'm going to put that in quotation marks because what do you mean by macroscopic? There's a unique macroscopic level of description. All of these things flow into the same macroscopic behavior. It doesn't really matter. Now, let's suppose that you say, well, okay, that's all very interesting, but I'm a high energy physicist, and my job is to go from the macroscopic world down. This is why high energy physics is hard. Because I can say, well, I'm going to derive a theory of electricity and magnetism. And it turns out that that theory of electricity and magnetism could be the one that James Clerk Maxwell developed, or it could be the Weinberg-Salam theory of the unified theory of electricity and magnetism and the weak interactions, or it could be a grand unified theory with electricity and magnetism, weak interactions and strong interactions and non-abelian engaged theories and blah, blah, blah. There's many, many different theories here, and you never know which one is. You can't predict it because it's not unique. And so the purpose of high energy physics experiment is to try to figure out, no, this one doesn't work, we've ruled that one out, this one doesn't work. So this one is right. Except that this one is just, and there's even more microscopic ones lower down. This is just the energy that you can see in a tunnel, 17-mile tunnel in Switzerland. Like if I could build a 100 million mile long tunnel, I'd be able to see all sorts of other physics. And so this hierarchical structure of science based on the levels of description and this idea of universality in going this way, that is a thing that's completely changed our picture of the physical world. So when you look at what Phil Anderson wrote in his lecture, in his book, in his article, he talks about the hierarchical structure of science. And if you think about this picture here, this to this to this, and so on, it's a hierarchical structure of levels of description. Okay, so this is why it took so long for the existence of atoms to be detected. We didn't know that atoms existed. 1905, Einstein wrote 3 important papers. Okay, one of those was the theory of special relativity. The other one was the one that he got the Nobel Prize for. What was that?
Photoelectric effect.
Photoelectric effect. And there was a third one. The third one proved the existence of atoms. Okay, it worked out the consequences of what was known as Brownian motion, and the predictions of that paper were detected by Perrin in 1911, and Perrin won the Nobel Prize for that. Einstein could have won another Nobel Prize just for that work. So we learned about the existence of atoms through statistical mechanics, through realizing we had to do that. So where do atoms and their interactions matter? The elastic forces are characterized by phenomenological parameters such as shear modulus that only can be computed from atomic level description. So I've got these springs, and you might say, well, what is the spring constant of these springs? Okay? I'm a physicist. I have nickel. Okay? So I'll go and ask a quantum chemist. And the quantum chemist will work out what are the actual interactions between these atoms for whatever is the particular material, and they can actually compute what those spring constants are. As a physicist, I don't know what they are. People like Poisson and Cauchy and Maxwell just said, well, there's some spring constant. Let's call it the shear modulus. Let's call it the Lamé coefficient. Let's call it the Poisson ratio. Those were just numbers characteristic of every material that they could measure. We can't compute them. They didn't know where they came from. Now that we know about atoms, we can compute them, but you can compute them starting from atoms, from the building. If you ask a high energy physicist, can you compute them? The answer is no, obviously not. You'd have to compute all the quark and gluon and stuff like that. So you do need to be able to take these phenomenological parameters and tell you about what's happening at the level you're interested in. And the values of the parameters that produce the spring constants that tells you about the physics at the small scale. Now, one of the things that we're not going to talk about so much in this course, but we'll talk about a lot in next quarter, is emergence leads to generalized rigidity. The generalized rigidity describes the response to perturbations. So in this particular case here, when we think about this material as being rigid, we know that if I hit it, it'll wobble and produce sound waves and so on. If I compute even further, I'll know how hard can I push it before it breaks. Okay, I can look at plastic behavior and so on. So this rigidity, this aspect of a solid, happens not just for something turning into a solid. It happens in magnetism, it happens in superconductivity, it happens in grand unified theories, it happens in string theory, it happens in the formation of order in the universe, it happens in fluid mechanics, it happens everywhere. So there's this sort of generalized rigidity describing response to perturbations, and we'll work out how to understand it. It happens in biological systems. In biological systems, this is called resilience. We want to understand how resilient are biological systems. How well are humans going to work when the average temperature has risen by, say, 3 degrees, and the extreme temperatures have risen by 10 degrees? Okay, you can't even, in some parts of the world, will be unlivable. The biological resilience is an aspect of this. So what I've told you is emergent levels of description absorb properties of lower levels of description into phenomenological parameters, typically a small number if they're going to be useful. That makes fundamental physics hard because one goes against the flow of emergence. So the whole reductionist program, the idea that we just find out what stuff is made of, then we understand how stuff works, completely wrong. Not just wrong because it's like silly, like you see all the springs and cogwheels fly out of an old-fashioned watch and saying, right, now I know how a watch works. It's even worse than that. There's not even anything unique that comes out of it. And then trying to understand collective properties of matter without requiring knowledge all the way down. And that's what we do in physics. So we have to be careful to understand the right questions. Okay, so let's try to summarize some of these ideas. So we've talked about emergence as being associated with a loss of uniqueness. What do I mean by that? Well, if I take a fluid and cool it down, it's still possible it could stay a fluid. There are some fluids that you can cool them down below the melting temperature and they'll still stay fluid. Okay, and then if you click them like this, then they'll suddenly pop and turn into a crystal or something. So a fluid state is still possible at low temperatures, but much less likely than the solid state. So there's a loss of uniqueness there. Phase transitions separate these different states, and they're collective. They're only well defined for thermodynamic large systems, and we're going to learn how do we understand how emergence arises, how phase transitions occur. And then these new collective phenomena arise. Okay, so what I've told you then is emergence in some sense is the hallmark of complexity. So you might say, well, okay, so we know that our world picture is you have atomic physics and condensed matter physics. And then if you want to look a bit bigger, you might have, say, cell biology, and then you have the tissues, you have organisms, you have multicellularity, biofilms. Those organisms can create ecosystems, they can create community structure, social systems, economic systems, and so on and so forth. So that's a kind of hierarchy of complex systems. And you think of it, emergence as really happening there above the level of condensed matter physics, just as I told you. And you can say, well, I have emergence, I have some order, but seeing an ordered crystal, seeing a superconductor, is that really complex? Not really. It's complicated, but it's not really. Doesn't have all the hallmarks of complexity that we've talked about. So complexity is some sort of secondary phenomenon as part of emergence. So you could say, well, emergence begins with strongly interacting condensed matter physics. We should all go and study condensed matter physics. Or does it? Let's have a look at atomic physics. So we go and look at atomic physics, and atomic physics is just this bit. But then you have atomic physics, nuclear physics, quarks and gluons, whatever, grand unified theories, or so on and so forth, superstrings maybe. There's emergence at every level of description. So you might say, well, are the most fundamental interactions emergent? Okay, Let's talk about string theory. People thought there was going to be a unique theory of strings. When I started my career as a faculty member in physics in the early 1980s, mid-1980s, string theory was just being started then, and all my friends who were doing string theory said, this is the ultimate theory, unique theory of quantum gravity, blah, blah, blah. Maybe 20 years later or so, 30 years later perhaps, those same friends told me, actually, this theory that we thought was fundamental and unique actually has 10 to the 500 ground states. It's emergent. It's not the true ultimate theory of everything. Okay? So everything is made up of stuff. And how you resolve that philosophically, I don't know. If you want to read an essay about that, I'll put it I'll post it on Teams. There was an essay I wrote last year for a book called 50 Years of the Renormalization Group. And the book is called, the story, the article is called, actually, what is it called? There's More Room in the Middle, or something like this, which is a paraphrase of a lecture given by Feynman. And it talks about exactly this whole issue of how you think about fundamental interaction. Okay, what is emergence? I've told you a little bit about what emergence is. Let me tell you about what emergence isn't, to inoculate you against some of the nonsense that you will read if you read, say, the popular science literature or sometimes other literature, like Wikipedia even. So sometimes people say emergence is something where it's surprising and unpredictable. If something happens, you didn't expect it, and that's what you mean by emergence. That's completely wrong. Okay, that's absolutely not what emergence is. In the systems I'm going to teach you about in this course, the next course, we understand exactly how emergence happens. We can quantify it, we can predict it. There's nothing surprising and unpredictable about it. It might be surprising if you don't know graduate level physics, but it's not surprising, it's not unpredictable. If you can't predict it, it means that you just don't have enough information about what is going on, which may be true, for example, in climate change, looking at tipping points and so on. So the subjective difficulty of a calculation is not part of the difficulty. So here's another thing. People sometimes say, oh yeah, I know what emergence is. The whole is greater than the sum of its parts. Okay, you've heard that expression before? Yeah, yeah. So that means emergence. Well, no. All it means is that if I have a system that is non-interacting, then its energy is just the sum of the energy of the individual particles. If I have a system which is made up of interacting particles, then the energy is not the sum of the energy. It's the sum of the energy of the individual particles plus the collective part of their energy that comes from their interactions. Okay, and there's various names for this and so on. But I can compute that and still not have emergent properties. So this does not necessarily lead to emergent behavior. So it's certainly true that you do need interactions to give you emergence, but having interactions is not on its own sufficient to give you emergent behavior. It's necessary, but not sufficient. So you could take a bunch of particles, ideal gas particles, they're flying around, you put interactions between them, and then you have a modified equation of state. You have, say, the van der Waals equation of state, or the Leonard-Jones equation of state, or something else. That might perfectly well describe a fluid. It doesn't necessarily describe a solid. And then the other thing is, I'll just go through this one quickly, is that what we mean by emergence is that when you have an emergent state, it exhibits some sort of generalized rigidity, an outcome of the collective interactions between the components that was not there before. Okay, in this quarter, we're going to talk about the onset of emergence, scaling, phase transitions, and fluctuations. So here is a phase diagram that you may have learned on your mother's knee. This is pressure, this is temperature, this is the solid phase, the gas phase, the liquid phase. Now this is the line of coexistence of the liquid with the gas, and this is a critical point. And beyond this line, beyond this point here, there is no line that separates the liquid and the gas phase. And we're going to talk about that in detail next time. So that critical point is where second order phase transitions happen. And that's where we're going to be focused a lot in this class. Why? Because when you have a critical point, turns out you have large density fluctuations So here is a picture of a fluid near its critical point. It's a simulation. The black means regions of high density. The regions of white are regions of low density. And as you get close to the critical temperature, what happens is the system looks the same on all length scales. It becomes scale invariant. And we're going to try to understand this scale invariant. This scale invariance is the property of phase transitions, which inspired the most interest by physicists because it was so hard to understand. And it was hard to understand because there's no small parameter there. Now, when we talk about emergence, let's go back to our example of the magnets that I've erased from the blackboard. So this is the magnetization as a function of temperature for a simple magnet in an external magnetic field. Near this critical temperature, where the magnetization goes from being 0 to starting to be a magnetic system, this is 0 temperature. This is critical temperature. This point here is non-critical. This is where we're going to be spending all our time in this course. Okay? We're going to try to understand what happens there. And what happens there turns out to be really strange, very counterintuitive, and it helps us understand complex systems. Let me show you some experimental data. So there's the picture I just showed you. This is the magnetization as a function of temperature of H is equal to 0, no external field. If I ask you, how does the magnetization scale with the distance, temperature minus the critical temperature, as I go below here? Okay? So let's make a simple theory. Let me do it over here. Let's make a simple theory of this phase transition. Okay? So this is going to be the easiest calculation that we've ever done. Let's see how it goes. So the question is this. Here's the magnetization. Here's the function of temperature. Here is Tc. And then what happens is as I go below Tc, the magnetization changes. And so it goes up. This is the magnetization of spin, go 1, 0. So the question I want to ask is what is the behavior? Here, I want to know M, where is the Tc minus T over Tc? How does it behave? Okay? Let's make a simple theory. Remember to do it, I give 10 seconds to make a theory of this basement. We should be writing. We've got 10 seconds to do a theory. You can see it. And make a theory. You can do it. Okay. All right. Anybody figured it out? Okay. Let's say linear.
Yeah.
Okay. You might say, well, maybe it's a parallel.
Yes.
Okay. I'll tell you what was parallel. It is 0.3 to 4. How many people got this? And remember. Okay, let's do the theory. Here's how you do the theory. Okay? So what you do is you say, let's take this graph and switch it upside down. Okay? So here is going to be n, and n of course can be negative as well. So let's do this graph with this. This is the temperature, and then this what I've drawn you. If this goes like that, and then I could draw the other one. This would be another image. So let's change the question. Let's not try to work out what n is as a function of t. Let's try to work out what t is as a function of n. What do you think it's going to be? Well, let's do a Taylor expansion around here. So it's going to be Tc, take the n is 0, and then it's going to be something else. Well, this is an even function. So the next order correction must be some alpha times m squared. Okay? Everybody agree?
Yeah.
So now let's rearrange this. So that gives me the n with the Tc minus t with the Tc to the 1 That's the 10-second theory for this phase transition. It's fantastic, isn't it? All I used was symmetry. And I got this prediction. And yet, I'm telling you that the answer is actually something like this. How is it possible? How can this simple theory, which assumes virtually nothing, how can this possibly be wrong? How can it be wrong? Okay? This was the question that Landau couldn't answer, finally couldn't answer. None of those famous philosophy you all heard about in textbooks couldn't answer. We only learned the answer to this about emergence. Okay? This is why this is so interesting. Okay? This is a problem where it's like, it's not a question of where okay, maybe I got 0.45 rather than 0.5 or something. It's like, we can't even understand in principle. No, this could possibly be wrong. I assume so little. We assume virtually nothing. Okay, so I'll leave you to think about what went wrong there. And I'm going to show you, and we're showing you something even more amazing. If I sit at the critical temperature and only measure what happens as you apply an external magnetic field, you would think that the magnetization is but it's not proportional to this. And we're going to have, and we'll see, we're just finishing. We're just finishing. The next, this lecture hasn't finished yet. It'll finish in 30 seconds. So what's happening is that this is a breakdown of linear response theory. And what we learned was that in fact, this linear response theory breaks down in an interesting way. Here are data on all different magnetic materials, magnetic materials, functional magnetization as function of external field and temperature, all those data plotted against the way that the normalization group predicts. And all those data fall onto one universal curve. And you see there's a line going through these data points, which is a line from theory. That curve has no adjustable parameters, and it precisely agrees with the experimental data. So what I'm showing you then, we have a picture, model of phase transition, which gives a precise prediction in agreement with experiment. Okay, this is what I'm going to leave you. It's not a model. The model. This model is so powerful that it gives you a prediction, which is a precise agreement with the experiment, but it's a model that starts off with quantum chemistry, went to electronic structure, then to quantum Heisenberg spin models, classical Heisenberg spin models, Landau theory. We talk about all of those things. Every step along the way here were approximations that made no sense and could not be justified, and yet gives a precise prediction in agreement with experiment. Okay, so that's where we're going to finish. That's the end of today's lecture. Next time I will begin. I just want to tell you that this is what we're going to be talking about this quarter. Next quarter, we talk about the properties, the universal properties of our but for now, we're just going to focus on that. Okay, I will be in touch. Please make sure you've joined Teams, and I'll see you on Wednesday.